So the next speaker for this session is Krishnan, and he will be talking about Byzantine distributed function computation.
Thanks for the introduction. This is a joint work with Neha, Varun, and Vinod. So distributed source coding is it's a classical problem in information theory. If for the new students, if you take a course in information theory, you will just come across this thing. If you've already seen information theory, you know there are a bunch of users connected to a decoder, and they all get random variables which are correlated from a joint distribution. These observations to the decoder, but not in full length. They're free to compress it and send it. And the decoder says that the rate region, as in the amount of rate for which this is possible, and if given a rate, how can you do it? This thing was given by Slepian and Wolf in 73. It's a classical result. There is a different flavor of this problem, which is called the function computation problem. Here, there is a function f, which is the function of all these input variables. And you would like to compute, the decoder would like to recover the decoder would like to recover the function. So it can output some estimate of that function. There is a lot of work in this area as well by Binder and Ziv, Berger, Tung, and Corner and Martin. And this is, in general, it's an open problem, as in what are the rate regions for given a function, what are the rate regions that can be obtained. It's, in general, it's an open problem, but some special cases have been solved. What we solve here is, what we want to see here is a special case of this function computation problem, but which is a Byzantine distributed function computation problem. So what is this Byzantine element? The Byzantine element is the following. There's an adversary who is allowed to corrupt a bunch of these users. But what does it mean? It means that the adversary can look at the observations that the users get. It can jointly compute some function of these observations, and then it can dictate what these users are going to send. And the decoder's goal is the same. It wants to recover the function. It wants to recover some function f. The question that is interesting in this case is what functions can be recovered. In fact, the interesting question would be, given a function, what rate regions can be recovered, but can you even recover certain functions? It turns out that certain functions are completely impossible to recover. So even without any rate limits, can you even recover certain functions is the question that we ask. Rate region just means that for a given function, for in this case, what rates that these parties would have to use. So rate is, so these parties are communicating in blocks, and if the block length is r, then the rate is n by r for that party. So the rate region is the like the set of all these. Oh yeah, sorry. So I forgot to mention why the decoder has some side information, y, which is also correlated with the original information, the original sequences that the users get. Adversary cannot corrupt y. Yes. Yes. It cannot see y. Adversary can only see the inputs of the users it is corrupting. Yes. No. So in this picture, the adversary is not corrupting x1. Sorry. No, in this case, it can be up to k minus 1 corruptions. So we have a general characterization in that sense. Sorry? Yeah. So we'll, when the n is 1. I mean, all these results are in asymptotic, so I'm not sure if n is 1, what would happen. Like, Uh,
I wanted to compare it for
yeah, 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 yeah. What functions can be? Uh, yeah, I'm pretty sure there are some simple examples that we can look at. But yeah, I don't have anything top of my head right now. Okay. So yeah, so what is it? So what is exactly the decoder trying to do? The decoder is trying to recover the function, but what does the recovery mean? The recovery means the following. With high probability, the decoder should be able to output a corrupt user's index if there is any corrupt user. Or if it is not able to find any corrupt users by whatever algorithm it is using, it just outputs a string such that the output string is very close to the actual function that we want to compute. And in this particular case, we are looking at Hamming distance, Hamming closeness of the strings that the output and the actual function has. If there is some more related work, I'm skipping that slide. So let us look at some simple cases to understand what sort of protocols can work, which is also the existing work. So the simplest scenario is where there is only one user who is connected to the decoder. And this user can be corrupt or can be honest. These are the only two scenarios possible. So the decoder either blames the corrupt user if it is corrupt, or it outputs a string if it is not able to figure out if it is corrupt or not. It just outputs a string. And we want to characterize when is this output string very close to whatever it has output, whatever the function is. So in order to look at this, let us think of this simple experiment where we take two, so X, the script X is the characters of the input. We think of this simple experiment where little x and little x prime are two different letters in that alphabet, such that the conditional distribution of y given little x is equal to y given little x prime. And the decoder cannot catch who swapped x with x prime because all the decoder has access to is the conditional distribution. And they just look the same. Doesn't matter if x was sent or x prime was sent. This idea can be extended directly in the following manner. If you look at the entire alphabet of x, we can make these partitions based on what characters have the same conditional distributions. For any two characters which have the same conditional distribution, they belong in the same part. And this partition further induces, it naturally induces a function of x. I'm going to denote this function by x down arrow y, because it's a function of x, but it's also dependent on the joint distribution of x and y. This is called the minimum sufficient statistic of x with respect to y. And it is pretty clear that the decoder cannot learn anything more than the minimum sufficient statistic, because you can just swap anything and the decoder won't be able to figure out. So this is at max what the decoder can learn from x. And therefore, the function that the decoder which it can learn with y as well is some function of the minimum sufficient statistic and the side information. And it turns out that this is a tight characterization. So every such function has a scheme. There is a scheme with such that every such function can be recovered. And this was given by Fitzy, Wolf, and Goldschlager in Crypto 2004. Now let us look at a two-user case. And Narayanan, Prabhakaran, Sangwan, and Watanabe in Eurocrypt 2023, they gave a scheme so they gave a family of functions which are recoverable and a scheme for that. To understand this scenario, let us just look at the simple experiment again, where out of the two users, so there is only one party who is corrupt. The experiment goes as follows. I'm going to block user 2, And I'm just going to assume that the decoder is only communicating with user 1. It can trivially, using the idea that we just saw in the previous scenario, it can obviously learn x1 down arrow y and y. It can learn any function of that. But now what the decoder can do is it can actually learn much more than this. It can assign, it can upgrade its side information, its own side information with this new variable, which is the old side information, which was y, and the new side information and the new verified object, which is x1 down arrow y. So this new verified object is the new side information, and it just does the same experiment with user 2 by blocking user 1 with this new side information, and using the same one user algorithm, it can again learn more information about user 2. So that new information is now, we are calling it x2 down arrow y1. And then the decoder upgrades its side information with this new thing. So now the side information is y and x1 down arrow y1. Sorry, that should be x1 down arrow y2. That should be x1 down arrow y2. And then it does the same experiment with user 1, blocking user 2. Then it keeps doing it again and again until it stops. But does it really stop? It does stop, because all the size of the characters is what the bound, what decides the bound of how many steps it goes. And this final random variable, which the decoder is able to verify, is y star, and f is recoverable if it is a function of y star, because it can just naturally recover using this algorithm, right? Excuse me?
Can you repeat why?
It stops because the characters on x1 and x2 are finite. So at most, the number of partitions that x1 and x2 can have is the number of the size of that character, the product of the size of this. A similar scheme holds for any number of users. This is something that we have, but unfortunately, it doesn't extend to more than one corruption. So now I'll get into our characterization. So we asked the simple question: if f is recoverable, what form it should be? And to see this form, let us look at this particular setup where assume that party 1 was corrupt, and user 1 is corrupt and user 2 is honest. And it generates this distribution Q of x1 bar, x2 bar, y. And think of another scenario where party 2 is corrupt, but party 1 is honest, and it generates the same distribution. So once you have this distribution as the view, same view distribution, when you have this view distribution, it is impossible to figure out which world it was coming from. And for any function such that the original variables x1 tilde, x2 bar, y, and x1 bar, x2 tilde, y, if they have the same value, if they are equal, then this function, the function which can be recovered must have this form. This is just the same experiment written in some language here. Yes. Sorry, this particular, yeah. This converse, yes. This is a general converse. This is a general characterization. And then naturally we can ask, is there a recovery scheme for all such functions in F? So this family, I'm calling this family as F. And it turns out that F is exactly what the Narayanan et al. Paper had mentioned, which is the y star variable. So every function has to be a function of y star. But of course, their thing doesn't extend beyond one corruption. So we need a protocol for a general corruption. So let's see that. Okay, so before going into a protocol, we the decoder, so there's an alternate way of writing the characterization, which is a decoder friendly way of writing it. But this is just it's just another way of writing it. So this is the algorithm. In the first step, the decoder receives the sequences x1 bar, x2 bar, and y from the two parties and its side information, and it computes the empirical distribution p of x1 bar, x2 bar, and y. In the second step, the decoder prepares some sets. Now, what is a set? This set is a set of all possible view distributions that can be generated when party 1 is corrupt and party 2 is party 1 is corrupt and party 2 is not, because there's only one corruption. Similarly, you can also generate the sets for the second party being corrupt, which is the script v2. In the third step, these sets are expanded in total variation. So you generate these sets v1 delta and v2 delta. And in the fourth step, we just want to check where this empirical distribution lies. If it lies in v1 minus v2, then it is probably user 1, because this is the set of all those distributions which user 1 could have generated, but not 2, but like with a total variation gap. And similarly for user 2, if it is in the other side, it's probably user 2. But what do you do if it is in the intersection? It could be that user 1 has generated, it could be that user 2 has generated. So you don't know which one, which user is the corrupt one. So you just output the original function f on the sequence that you received. And this thing works. Yeah, so there is just some technical why this scheme works. This scheme works because, if you consider one particular attack which is very close to the boundary, so user 1 attacks with a mounts an attack which is very close to the intersection, but due to the typicality noise, because empirical distribution is not the same as the output distribution, it is quite possible that the distribution that you perceive is inside, the decoder perceives is inside the intersection, but it's still okay to do. Even if it was not supposed to do it, it was not supposed to output a string, but it's okay if it outputs. It doesn't get a lot of error. And that's the main idea that we use. And that's it. Some more comments. We characterize the class of recoverable functions. A technique generalized to any arbitrary adversary structure. Achievable class of functions in the case of at most one corruption is tight. This is the comment that I mentioned. And a function's recoverability can be checked using a linear program. Some additional. Thank you.
Are there any questions? Actually, I had a question. There's something about the expansion by TV distance.
Yeah.
Can you use any other statistical distance? There's something.
I think so TV just turned out to be the right thing to do. Yeah. I think we did at some point we were looking at some KL divergence based thing, but for some reason it did not work out because of some support issue. I don't quite remember at this point. Yeah, it just worked out. Thanks.
Thanks.